Hey there, ladies and gents. Okay, sorry we didn't get to finish this in class, but that's the nature. Sometimes it's really heavy geometric work. Like we just don't really have enough time in class to do it, unfortunately. So, thank you for watching this and updating your notes. It's going to make sure that you're going to make sure you're prepared for next time you meet. And that's always a really good thing, right? So, my goal is twofold. I want to make sure I finish these notes for you, but also I want to make sure that we're talking about similar things next time you meet. So try to shed some light onto this really heavy concept that I'm pushing forward. This idea that when you argue geometrically, like you're never arguing directly, you're always arguing from a different angle. And it's never based on your opinion or because you said so or because you think it is or you want it to be, but it's always based on some other fact, some other thing. I use the analogy of like some friends in a group trying to convince, or trying to get these two people together, but there's always go-betweens, and that's really the point of this, is that if you want to accomplish a goal in geometry, you often have to find a go-between to help you do that. So the goal of this sheet is provide for you maybe beginnings of a nice little toolbox where when you're doing some work in the future and you're asked to say, cut an angle in half, make a perpendicular bisector of an angle, you'll realize that you just need to find the constructor you already know and use it in the proper way. Okay. Anyways, let's jump into it. Let's see if you guys can get a sense of what I mean. So I'm going to go from the beginning, even though I know for most classes we got down even to like the bisected angle part. But it's always good to review, and that's what I'm going to try to provide for you, just a little bit of review. So let's go. Anyway, so I'm probably not going to fill out the because part. I'll leave that to you to kind of analyze and fill out. So let's talk these first two columns. So to prove a single distance, we stated in class, and you guys also agreed that all we really need is one circle. Okay, and I know we can put arc there as well. Arc is just part of a circle, so we don't have to draw the whole thing, but understand that we actually do have a circle at play here. So why is that? I'm going to try to draw this. I'm using my mouse on my computer, so forgive me if it's not the greatest. But here is kind of a sense of, here's kind of the reason why. Let's say we have this line, and we want to copy the distance. The distance is devoid of any kind of orientation, meaning we don't really care which way the line's pointed. We just care that we're copying, or I'm sorry, that we're doubling the distance or copying the distance. So I'm going to put a point there to mark my center. And so if we just take a single circle, mark it at the center, and then pull this out, we've created ourselves a distance. I know that's not perfect. Again, we're just kind of representing here. So let me grab this center point as well. Oops. So if I were to replicate this circle somewhere else, and again, it wouldn't even matter where else. Just taking this circle, now that I have this distance set, and say putting it here. A circle is enough because we don't really care how it's oriented. As long as it's starting in the center and then pulling out, we can actually put that line anywhere because of the properties of circles. So that's why a single distance actually is enough, because all we really are copying is this radius value. So I can put it here, and it's a copy, I can put it here, it's a copy, I can put it here, it's a copy. But again, a circle is enough because I just want the distance, okay? So let's go back here. Okay, so that's why one circle is enough because again, distance is all they really care about. So a quick no representation might be something like this. Like all they really care about is a radius. Like that guy is a radius. When you get into something a little more complex, a fixed point, it's a kind of a whole new ball of wax. Because a point is a location, we can't simply use a single radius. So this is no longer any good. But if I introduce a second circle, now I'm in business. So like if I have circle number 1, let's change up colors, and then let's add circle number 2. This is good because I do have 2 points of contact here. And if I have 2 points of contact, I can fix the locations. So if I take these 2 points here, I mark them with daisies. Well, the reason why this is a fixed point is because if I consider the center of this circle out to either one of these 2 points, they're both going to be radii of the black circle. But if I add to that the radius from this teal one, that daisy, the one I'm pointing at right now, represents one of only 2 places that is exactly the blue radius and the black radius away from the centers of the circle. The other one being this point, which is more or less a reflection point for the other one. So these two daisies, again, represent the only 2 points that are simultaneously at the same time teal distance and black distance away from the center circles. If I take, like, say, this radius, I can put it anywhere on this circumference, but it's not going to meet the blue circle requirement. That's why using two circles to fix a distance is so genius, is because it keeps it exactly where it should be, and doesn't move, and it's impossible to move because again you're locked by these radii. So I can't pick like this to be the intersection because, well, besides the fact it's no intersection there, it's only the black radius apart. Okay, so that's ultimately how and why, I should say, why two circles are required to fix a distance. Of course, you can just say two arcs because it's only a couple points of intersection that are even possible. So if I take like circle 1 and then introduce circle 2, these are the only 2 points that are simultaneously, in this case, the red radius, that's supposed to be red, the red radius and the purple radius away. That point, of course, the one at the bottom. That's it. And so this is how we can make sure points don't move, because so you can only have, under these conditions, there's only 2 possible sections. Parallel lines is where we started to part a little bit. We're kind of looking at this in a more advanced way now, because again we have this module bringing in. So if I want to fix a distance, the module I'll bring in, or the idea I'll bring in, is using a single circle. If I want to fix a point, I'm going to use 2 circles. If I want to use parallel lines or create parallel lines, the thing I'm going to bring in is an isosceles trapezoid. Now we saw a specific example in class where we're trying to prove a trapezoid is also parallel, but in the end, I don't want you guys to kind of glass over this point, but in the end, it's really just about parallel lines. So let me try to explain what I mean. So let's say I have this line, and let's say I fix a point or pick a point right here. Okay, let's say I want to create a parallel line that goes through the blue line, or through the blue point. I can do this. I can actually do this really easy if I just bring in the isosceles trapezoid idea. So I'm going to kind of freehand this, but you guys will definitely see the point I'm trying to make here. So if I construct a isosceles trapezoid, that's going to be the thing that gets me the parallel lines. So I'm going to copy this distance here. Again, just kind of eyeballing it because I don't want to take any extra time here. And then I take the distance from the other end to the blue line. And I could do this with a compass, but we're just trying to give some understanding here. So, but then I take it to the other end line. So now I'm using two distances, the black and then the orange, to fix a new point. So the other intersection would result in the parallel line. So this guy right here. So again, if we can identify clearly what we're trying to do, which is construct parallel lines, excuse me, it's really just a matter of understanding the points we need and then using the correct technique to get those points. So in the end, oops, sorry about that. So in the end, even though we just had a line and a point, if we construct the isosceles trapezoid over the top of it, we are good to go. In fact, let me go ahead and show you what I'm talking about. So this isosceles trapezoid right here is what we just constructed. That's what we found by finding this point. But the important part of this was actually that we ended up with parallel lines. So isosceles trapezoid is a thing that gets us parallel lines. So like in the future, if I ask you, hey, I need you to construct something that's parallel, the first thing that should pop into your mind is the thing that gets that done for me is isosceles trapezoids. So we can record that. In fact, I'm going to do a little differently than maybe I offered in class. So if I have this set up, What I really need to do is over the top of that setup, construct an isosceles trapezoid. Because if I do that, I should end up with a parallel construction. Because an isosceles trapezoid, that line is certainly parallel. Excuse me. Okay, so if I want parallel, isosceles trapezoid is the thing that gets me that. In terms of perpendicular, we can kind of think in that same way. Now, in class, we talked about really just constructing a kite. So I have this line, and I have, let's say, this point, and I want to end up with a perpendicular one. What I really need to do is construct a kite over the top of it. Because if I do that, and again, using kind of the kite construction, so like we need a couple circles to make this happen. But if I use a couple circles, thus transferring some distances and keeping like arcs the same, I should end up with a nice perpendicular construction. And that is all the result of me constructing this kite. So just like with the parallel lines, if you want parallel lines, think isosceles trapezoid. If you want perpendicular, think kite. Right? Perpendicular bisector. Now this is, if you're 4B, we didn't quite get to this one, so this is going to be kind of new to us. But I can go ahead and tell you that if you're interested in a perpendicular bisector, and do keep in mind the term bisector means to cut into two pieces. So like if I have a line segment and I want to bisect it, what I mean is cut it in half. So those two sides are the same length. Okay, so like if the whole pink line was 15 inches, this is 7.5 inches, this is 7.5 inches. Bisect means to cut in half. I should say cut into two congruent pieces. So if I want to make that happen, so if I have this line and I want to cut it exactly in half, the construction we're going to make is an isosceles triangle. Okay, now you might be saying, oh, okay, that's weird. Like, why would you do that? Let's go to our big screen here, and let's recreate it. Okay, so I have this line. I want to cut it exactly in half. I would claim that what we actually need to make is a isosceles triangle. Let me explain what I mean. So if I take this piece and I cut an arc, or cut a circle, and then I take this exact one again, so it's copy and pasted, but centered over the other endpoint, I create for myself two points of intersection. But the important thing to note here is that since these points of intersection actually are radii, so that's the radius of the circle, it appears in two places, one here and one here. Now, I actually misspoke there. It doesn't actually appear in two places, it appears in four. But since this circle was the same as the first circle I used, then all four of these radii have to be the same. So like this is like so like this piece right here is a radius. This piece right here is a radius, that's a radius, and that's a radius. So just like the kite, where this type of construction ended up with 2 points that are one on top of the other, equal-sided on either side of the line, same is true here. And so if I connect these 2 points, boom, boom, I should end up with a perpendicular bisector, where this distance is the same as this one. Now the triangle I'm talking about, like if we kind of lost perspective on that, the triangle I'm talking about is actually right here. Okay, so if you want to construct a perpendicular bisector, all you really need to do is construct that red triangle. With a point that's reflected below it, you can actually have that perpendicular construction, which is ultimately what the question was asking. So when I say construct an isosceles triangle, that's what I'm talking about. Okay. So if I want to cut that in half, again, what I really need to do is perpendicular bisector construction. Okay. Now the triangle in question will be here, but this will give me those 2 points that will go, that will make a perpendicular bisector. Okay? Okay, sorry about that, guys. That was my phone. Got slightly distracted. I'm going to turn it down now. All right, so bisected angle. Okay, so again, this is kind of maybe a weird one for us, but what I mean is to take an angle and then cut it exactly in twain. So if I want the setup for this, what I'm looking at is basically something like this. So what I want to happen, and I will draw this in a second, but I want kind of that action to happen. I want to make this. Well, the construction here, I'll tell you, is actually just a kite. So let me show you what I mean. So if I just take kind of any random angle, I'm purposely making the two legs different sizes because I want to make sure that all the steps are really clear. All we have to do is to construct a kite. So the piece of the kite that we're actually interested in is this middle section. Like what we're really making is this middle spine. So if you can kind of imagine, and I'll free draw a kite here. If you can imagine what we're after, we're actually just trying to construct this thing. Because a feature of kites is that these two angles actually are congruent. So if we make a kite that kind of looks like a stingray or a leech. If I can make a kite over the top of this, I'm in business. So check this out. Here's how this looks. So first of all, I'm going to draw this circle. The reason for it is I need some kind of unique and equal starting points. The starting points in particular, what I'm looking for are here, boom, and here, boom. So I can kind of ignore the rest. And you can kind of see the kite being built here. So I really just need like these two pieces here, and then I'm good to go. I'll accomplish this by using circles again. That circle will kick out some kind of distance out. I'll keep it kind of small here. And then I'm going to take the same circle and center it over this blue one. So again, a copy and paste job. And about right there. Okay, so the line that will result from point A through here will actually serve as a bisector. Now, if you're saying, hey, Mr. Collins, where's this kite you were talking about? And you can't quite see it. Here is a kite. Okay. And if you want to get super technical, this is actually just isosceles triangle, and that's the perpendicular bisector through it. So there's lots of different ways you can look at it. In fact, this is the interesting part, like as you add more geometry knowledge, you're actually just kind of recycling the same ideas over and over again. So let's go back to this and record it. Okay, so what we're looking for here is a kite. So this is the first one that kind of establishes the first two arms of the kite, here and here. And then we're going to use a couple more circles using these as the centers. That's terrible. And these circles should be the same length as well, because again, using radii, these two radii should be the same too. And so now we have this perpendicular bisector that goes right through the middle, and that actually does finish our kite as well. So that we have our kite. So inscribed hexagon and inscribed square, no class got to these, and so there's going to be some vocabulary we need to clean up right away. The term inscribed, scribed means to draw, in means inside or internal, and so what this actually means is a hexagon drawn in a square, a circle, and the inscribed square is a square drawn in a circle. All right. So in terms of what this looks like, you have to understand like there's lots of different ways to kind of make this happen. But in the end, what you really should be looking at is that this is a series of old constructions we've already done. I'll start with a square, which I know is kind of the usual one to start with, because I'm skipping hexagon. I think that's more complex. But if I go to a circle, because I want a square drawn inside of a circle, I'm going to mark the middle first, which is something I haven't been doing up to this point. And then I'm just going to kind of draw a random circle. So if you kind of think about what I want point-wise, I do want 4 points, but I want them equally spaced around the circle. Because if they're not, it wouldn't really be a square. Let me explain a little bit more in detail what I mean. Like if I take 4 points, because I know there are four sides of a square, and I put it here, there's no way that's going to be a square because that side is going to be way long. They're not going to be 90s, and like there's not going to be the right configuration. But if I take those same points and I spread them out, okay, now I'm in business. So I kind of want 4 points that are directly one on top of the other. Think about what I just said. I want points that are directly one on top of the other. We've done so many constructions that are just like that. Um, like this, for instance, this kite. That perpendicular line used 2 points, one on top of the other. The fixed point thing, 2 points, one on top of the other. The perpendicular bisector, 2 points, one on top of the other. So I'm really this construction is really about fixing points one on top of the other. So I'm going to use either a kite or a perpendicular bisector, which is really just nice obviously triangle configuration to do it. So this is why this sheet is useful. Now I've been faced with a problem that I haven't seen before, but the answer I'm looking for is up here. Like which one of these constructions that I've already done will accomplish the job for me. In this case, it's going to be the perpendicular bisector. It's not going to be the kite because it's equally spaced. The kite kind of has that long tail. What I want is a perpendicular bisector. So that tells me really clearly what I need to do, because if I need a perpendicular bisector, I need a line to bisect first. Uh-oh. Okay, so I'm going to select the line here. And what I'm going to do is to create a line that goes through the center, because that's where I want my first 2 points. One on top of the other, right through the middle. And now I just need 2 more points that are like here and here. But again, a perpendicular bisector is that thing that does it for me. And so I will construct a perpendicular bisector. I'll use a circle tool. You could use a compass if you want. I'm just taking advantage of the tools I have at hand. So I'm going to take this, and I'm going to say go about right here. It doesn't really matter. I just need to make sure I'm using the same circle. So I'm going to copy and paste this guy and center it over my other endpoint. It's about right there. Okay. So I am doing a little bit of guessing. So forgive me if it's not perfect. Okay. So in the end, I do have my square. So I have these 4 points, 1, 2, 3, 4, and that makes my square. So again, even though it's a pretty complex construction, it boils down to using what we used before. So if I can come back here, go down to my square, my scribe square, the thing we're going to use is a perpendicular bisector. Okay, so the circle with the center. And then we're going to perpendicularly bisect that thing, and we're in business. Boom. All right. So last one, and I left this for last on purpose, is to describe hexagon. So we need a hexagon kind of drawn in a circle. Again, I claim it's really just boiling down to picking out the right construction, although this one might be the most unusual because there's just lots of ways to kind of do this one. I would say if you think about what you actually need to make this happen, you're going to need 6 points that are kind of equally spaced around the circle. And I'm not doing a great job demonstrating that, but I'm kind of eyeballing it. You can really kind of see which one's wrong. But again, it's all about the points. We've been talking about that for a month now. It's all about the points. So we need 6 points that are kind of like this. So if you're looking here, there's lots of different ways we can do that. Certainly one line right here would take care of the one through the center. But the question is, well, how do you configure these for. So I would actually think, or encourage you to think, about it kind of isolating it down just to like one piece like this. Certainly, if you made this circle, you actually do have a circle to work with. So because we had to take this radius, so I would maybe reuse that circle again and take that right to the center. Now you can see some of my points are pretty close. Okay, but it's not perfect. But I can reuse that again. So I'm using the same radius over and over again. Paying attention not to the points that I kind of guessed at, but actually the intersections of my circle. So I'm going to the center and going to that intersection, so that point's pretty close. Let's do it one more time. And I think you might see, you actually see the thing we're using. Now, you might be looking at this saying, oh, geometric flower, I totally remember that. Good, you should. That's actually the first construction we started with. Okay. Clear the email. Okay. So now the question is, well, what kind of configuration did I actually use here? And this one's a little bit hard to kind of track, but hopefully you're seeing this. Okay, so I have multiple radii, but it's coming all from the same exact circle. So the construction I'm actually using here is equilateral triangles. Or another way to think of that is just multiple fixed points. Like I'm using two distances, in this case the same distances over and over again, to fix one point at a time. But in the end, it's just multiple circles intersecting over and over. Now the key was I used the same circle distance as the original circle. That's actually how it worked. But in the end, it's just about fixed points. So I would say here, I'm going to mark down anything for the inscribed hexagon. It's just going to be fixed points. In other words, a flower. Okay. And so it's going to be super messy to try to draw. I'll do my best. It didn't turn out perfect, but you get the point. And then let's see. Let's finish off with green. Okay. So I hope those helped a little bit. Again, towards the end, I hope you're seeing, like knowing these up here, these basics. These are our tools. So all we're doing is reaching out and kind of grabbing the ones we need at that exact moment in time. And that's what we're going to practice when you guys come back to me tomorrow or on Wednesday. So again, hope this helped. Thank you for finishing your notes. Tell people that this exists if they need help. Direct them towards this. Let them finish your notes first. Thank you and good night.